This is the lecture for Module 6 of Unit 5. Unit 5 is on acids and bases, and Module 6 concerns polyprotic acids. You may remember polyprotic acids from your first general chemistry course. Let's begin by considering the example of sulfuric acid as an illustration. Sulfuric acid is a diprotic acid. It can successively lose 2 protons, as usual. The number of acidic protons is typically indicated out front. There are 2 of them. And successively means that, we can and will think of a sulfuric acid molecule as first donating an H plus to water to form bisulfate or hydrogen sulfate and hydronium. You know sulfuric acid is a strong acid, so it should not surprise you that K for this first dissociation is very large. We're going to treat it as an infinite number for our purposes. In other words, we can assume this reaction goes all the way to the right. The second proton loss, the conjugate base of H2,4 continues to act like an acid. The second proton loss involves bisulfate losing its proton to water to form the sulfate ion. Ka for this is only 1 times 10 to the negative 2. So this is bisulfate is technically a weak acid in this case. Although, compared to other acids, this is still a pretty big Ka. Right, consider the pH and sulfate concentration for a 1 molar sulfuric acid solution. Essentially, the best thing to do is treat deprotonation as it actually occurs, which is successive. So at the end of step 1, if you assume a hypothetical equilibration, before we move on to step 2, is 1.0 molar hydronium or H plus concentration. Step 2 is then the dissociation of the bisulfate. If we treat the bisulfate or hydrogen sulfate concentration as 1, and hydronium ion concentration is 1, this is the appearance of our ice table. We assume no sulfate concentration initially. Alright, this gives 1 times 10 to the negative 2 is x over 1 to 1, essentially, or the contribution to the hydronium ion concentration will only be 0.01. Alright, so the pH then is log 1.01 or negative 0.004 in this case. Alright. Sulfuric acid is a bit of an unusual case. It's the only strong polyprotic acid that you would generally be concerned with. Most polyprotic acids are weak. Ka2 is in general smaller than Ka1, and Ka3 is smaller than Ka2, etc. In general, contribution to H plus from second or third proton loss will be negligible. For an example, let's consider the arsenic analog of phosphoric acid, H3SO4, 0.5 molar solution of this compound, and we have K values for its dissociations down here. Alright, you should be able to attempt to find concentrations of HAOS4 negative and HASO42 negative. In other words, the conjugate acids of the first and second dissociations. We will also consider the concentration of the arsenic analog of phosphate, AOSO43 minus. Alright, you can attempt the first and second parts of this exercise highlighted in black before moving on. Alright, step 1 is just a weak acid ice table. K is 5.6 to the 10 to the negative 3. If we set up the ice table and assume x is small, we arrive at x squared equals 0.0, well, x equals 0.052 at this point. Okay, compared to 0.50, this value of x is too large to treat x as small. Therefore, the best approach is to address this problem with successive guesses. Okay, 0.50 minus x is not 0.50 to two significant figures. We cannot neglect x. Again, we take 0.052 as a first guess for x, which means insert it into the denominator of the ice table expression where previously x was neglected. K is still on one side, x squared still appears in the numerator. Again, solve for x and get 0.050. Reinsertion of that into the ice table produces the same value of x on the third calculator. Alright, this gives H2ASO4 minus is 0.050, and this will be part of our solution. Alright, we also have established a hydronium or H plus concentration of 0.050. Now that we have handled the first step, we move on to the second dissociation. The equation for that appears here. Here K is 1.7 times 10 to the negative 7. Alright, Ka2 is much smaller than Ka1. We expect the concentration of this step to the H plus concentration will be negligible. Again, as we've seen previously, our initial values of H2ASO4 and hydronium in the ice table are the values that arise from step 1. And we assume a hypothetical situation in which there is no HASO4 minus initially. Its concentration increases to x. Solve for x in this case, we get 1.7 times 10 to the negative 7, which is HASO4. Proton concentration as expected is still equal to 0.050. We do not need to consider the effect of reaction 3 on HASO4 minus and the proton concentration, since Ka3 is much smaller than Ka2. And we calculate a pH of 1.3 for this solution. Okay. This is formally the conclusion of the part highlighted in black. If you wanted to carry on and calculate the concentration of ASO43 minus, you could take this value of HASO42 minus concentration and this proton concentration, and you can insert into the equilibrium expression for reaction 3, and you could in principle solve for ASO4 3 minus concentration in this way. I will present briefly here another way of solving for the concentration of this species. Here I have written the equations for the successive 3 dissociations of this acid, each with their respective Ka values. Note that if you sum these 3 reactions, you get the acid in 3 waters goes to ASO43 minus plus 3 hydroniums. Right, this means that if we can find the equilibrium constant for that reaction by multiplying the 3 Ks together, that gives 2.7 times 10 to the negative 1 as the equilibrium constant. and at equilibrium that is equal to the concentration of this species times the H plus concentration cubed over the neutral acid concentration. Right, treating this concentration as 0.5. Sorry, that concentration would be 0.45, 0.5 minus 0.05 for the concentration of neutral acid. Oh, and I had to correct an arithmetic error here. Correct answer when multiplying the three constants together is 3 times 10 to the negative 21. Solution of this expression for x gives 1.1 times 10 to the negative 17, which is the concentration of ASO43 minus. Now, we would have obtained the same value if we had taken the information from step 2 and inserted it into the equilibrium expression for the third dissociation. You will see this way of finding the concentration of ions like this in other examples in textbooks. Right, this concludes this lecture on polyprotic acids.